In this clip, we will derive the concept of statistical ensembles and in particular derive the description of the so-called microcanonical ensemble. Before we start the derivation, we first briefly recap statistics. Given an observable A, the mean of this observable is given by the sum on all products Pi times Ai, where Ai is a particular measurement of the variable A, and the Pi is the probability to find that particular value. Now, if we take for the probabilities the least informed assumption, which means all Pi's are actually equal, then normalization of the probability, being that the sum on all n of P is equal to 1, tells us that P has to be equal to 1 divided by n, the number of realizations that we have in our experiment. Now, this least informed assumption is the assumption that we will take in the description of the microcanonical ensemble. In the microcanonical ensemble, we assume a system described by n particles, which has the total energy of E and which is enclosed in a volume V. Thus, the system is living in some area of phase space characterized by the constraints n, E, and V. Now, our task is to determine the size of this phase space in order to determine the number of states that the system can be. Now, this number is most easily determined in the quantum view. In the quantum view, the states of every particle can be described in terms of its eigenenergy epsilon I. Now, if we assume n identical particles, which are non-interacting, all these states are identical also for every particle. Now, if we want to calculate the total energy of the system, this is then just given by the sum on all I, epsilon I. Now, in order to calculate the number of states this system can be, given the constraint of constant E, the task just is to calculate the number of states that all add up to E. This number we will call omega, which is dependent on the constraints n, E, and V, equal to the sum on all states of Kronecker delta E, H, the Hamiltonian of the system. We just have derived the quantum partition function of the microcanonical ensemble. In the classical case, the Hamiltonian operator H hat is transferred to the Hamiltonian in phase space H of Q and E, and the sum on all states is transferred to the integral on phase space P and Q. Kronecker delta is now the delta function, but we have delta of H of P and Q minus E. Now we assumed that we have n particles in 3 dimensions, such that the integrals on P and Q are actually 3 n-dimensional Riemann integrals, which we will indicate here by d3np, d3nq. Now, in order to do the counting right, we need to further consider that phase space is quantized. From the Heisenberg relation, we know that the product dp dq is equal to h, meaning that we need to add a factor of 1 divided by h to the power 3n to the partition function. Lastly, we have to consider that quantum systems are indistinguishable, meaning that permutations between particles always give exactly the same state. Hence, we have to divide the classical partition function with 1 divided by n factorial, which takes care of the multiple counting that we would have otherwise. In summary, we just developed the concept of the partition function of the microcanonical ensemble, omega. The microcanonical ensemble describes systems at fixed number of particles, fixed energy, and fixed volume. There where omega just tells us the number of configurations that we could prepare a system given those constraints.